one will be the third topic. Is again for general non-circular shaft. In particular, and again for the third topic, is we focus on the hollow shaft of arbitrary cross sections. In particular, the hollow shaft has very thin wall. So this topic is the third one in this chapter, and we have a particular name called the thin walled hollow shaft. And why I want to emphasize on the thin wall, we have to make sure the thickness is very thin enough. That is the assumption. If the thickness is not thin, then the theory, the formulation we're going to introduce won't work. Okay, so keeping this in mind for the third topic, once you're going to apply whatever we're going to talk about, keeping that in mind, those things will apply to thin wall, very thin. And usually you may ask me how thin this would be, and I can say the thickness compared to the largest dimension is at least 1 order of magnitude smaller, which means 10 times smaller than you will be fine. Okay, so that is the one. So for this case, so the topic. So here for this case, let me redraw this one, but you can refer to these figures. So here we consider an arbitrary cross sections, and this is the shaft. So basically here is going to, for example, the length, let me say is equal to L. The length can be long, okay? And the thickness, and here I draw is here. Let me emphasize, the thickness across different parameters doesn't have to be uniform. The thickness can be changing. So here I emphasize like this. So here that is the thickness. Let me so x is the axial directions, and if we apply the torsion here, so again the torsion is in a similar fashion like that one. We simply apply the torsion is like this. Okay, so just like this. So basically this one is under static equilibrium. And the thickness so that is the first one we can try, and then further quantify the behavior of the shear stress, then we can follow up is this. The first one, I will give you the result first and then give you the reason why. The first one is the shear flow. In terms of the notation in our textbook, we're using Q, and by definition is tau times T. The T is the thickness. The thickness T is not uniform, equal to constant. Okay, so for this case, I'm going to explain why. And by looking at this diagram, and it's kind of hard to draw, but here you can see, simply is this, we take a thin strip, we take the strip and the shaft, and that with the width is delta x. And then I simply take out the AB, I take out this patch as a free body diagram. Okay, and that free body diagram, let me put it into here. So hopefully you know the free body diagram I'm drawing. So here for this side, this is the cutting. Hopefully you see this side basically is along the thickness. And then on the top and the bottom here, I expose is the two faces here. Okay? Two surfaces here. That be okay? Basically here is the thickness T1, here is the thickness T2, and T1 doesn't have to be equal to T2. So for example here, this is T1, and here is T2. Okay. So here, assuming the shear stress is tau. And for example, the tau at position 1 for the T1. And this is the shear stress, tau, and then we call the T2, tau 2. Okay, and now we can approximate is this. The tau 1 is the shear stress, multiply this slash area equal to delta x times T1. The bottom, this is tau 1 times T1 delta x1. So this is the total force exerted on the slash area. The similar way, the tau q times Tq delta x is the total force and exerted onto the slash area. Everything must be in equilibrium in this direction. So that means the two quantities must be equal. By force in the axial direction, so here equal to 0. So that means from here the tau 1, T1, delta x1, delta x, will be equal to tau 2, T2, and delta x. So therefore, tau 1, T1 equal to tau 2,